Thank you, Victor, and thanks everyone for being here at this time of the day. So the work I'm going to present here is mainly the work done during my PhD as part of NCSR Democritus and CSC at UTA, and part of it is also work that has been done under my work with Mr. AI Lab during this year and a half that I'm been there. So let's start, and the key questions that I would like to target in this talk is, first of all, what do we mean by assistive technologies and how modern assistive technologies can be benefited by human behavior modeling? How can AI enhance the scope of modern assistive technologies? And lastly, what are the limitations that we face nowadays and how we can tackle them and move forward in the future? So let's start and go deeper to the first question, which is what are assistive technologies and how they can benefit for human behavior modeling. And first, let's discuss what is human behavior in the first place. So as humans, we experience things in different ways, we think differently, and we react and express also in different ways. However, there are still behavioral patterns that can be observed across individuals or groups of individuals. So we could say that human behavior exists from these underlying population generic patterns, which at the same time, though, are being expressed in a very subjective and personalized and unique way. And that is due to the multidimensional effect that different stimuli have in our body and the way we express our behavior and the way we provide physiological responses. So in a very abstract view of and simplistic view of what is human behavior, we could say that there are three main components that consist under human behavior, and these are actions, cognitions, and emotions, and are being highly interconnected and and being affected with each other continuously. So this very complex and dynamic relation is what makes us receive the environment the way we do and react to it the way we do. That is, which is usually very unique. So what is human behavior modeling? Is using data relevant to a specific user and data coming from those mainly those three entities, which is cognition, emotion, and actions, towards detecting underlying conditions, predicting future behaviors, and providing feedback and insights and recommendations to the users that are being involved in the task. So human behavior modeling has been applied in a variety of applications, varying from well-being to finance and advertising. But overall, we can say that whenever there's a human or humans in the loop of some interaction, there is usually a human behavioral modeling component that tries to tailor the interaction towards that individual or group of individuals. In this talk, we're going to focus specifically in the first three categories mostly, and application relevant to those, that is well-being, smart driving, and smart rehab. So just to give you an idea of how popular these technologies are nowadays, this is just a brief, a small representations of the different companies that have invested time and money to build technology around this area of research. And to understand better the importance and how human behavior is being a major part of assistive technologies, we have to understand what are assistive technologies in the first place. So based on an early definition by the World Health Organization back in 2000, assistive technologies are any equipment or instrument or product designed to improve functioning of a disabled person. So that definition, as you can imagine, evolves as our understanding of what is a disability evolves. So there are some major characteristics of a disability. It affects either our physical or our cognitive functioning, or sometimes both. And it can have an impact of our daily living. This impact can be minor or it can be major, and it can be permanent or temporary. So these are some generic characteristics, but as we better understand human nature and how it is being affected by our daily living, which is ever evolving, especially with the great impact that today's technology has in our lives, the definition of assistive technologies and disability and what is a disability also change. So a more modern definition by WHO is more like that. It looks like a text, and this is just part of it. And it still has a paragraph mentioning the importance of assistive technologies being applied into people with specific and diagnosed disabilities. But also there is this component that says that the primary purpose of assistive products is to maintain, improve an individual's functioning and independence, thereby promoting their well-being. So what I think it's a better fit for what we envision of assistive technologies for the future is any type of technology that aims to support and augment human capabilities towards enhancing their performance. So this can be towards tackling a diagnosed disability or anything that prohibits an individual from thriving in their daily lives. So assistive technologies have been applied in a variety of domains, from education to medicine to accessibility and autonomy to well-being, with both the private and the academic sector investing a lot of time and money in these areas. And to give you an idea of how futures and today's assistive technology is being perceived, I've built this toy example that can better describe what the capabilities of these technologies are. So let's assume we have Mary, who is an engineer. She's an amateur athlete. She likes to run. And also experiences mild PTSD symptoms. So she wants to participate in a marathon organized by her local city, and she's training for that. So her average performance is running about 3 miles in a 35-minute period. That is usually the case, except when she observes some changes in the daily routine of the past few days that have to do either with the regular work schedule, with her dietary or sleeping routine, or with the severity and the frequency that she experiences symptoms related to her disorder. So taking all this information into account, we can ask a bunch of different questions that can help this individual improve their daily living. That questions may relate to how she can become a better athlete, how she can become a better professional, or how her daily routine can be optimized towards her taming the symptoms she has from her disorder. How we try to do that is by exploiting devices that we use anyways in our daily living, that provide us with fine-grained, measurable signals, and using those devices trying to ground more abstract meanings and conditions like anxiety or stress or mood or performance that are hard to fine-grain by themselves. So what has really changed in assistive technologies during the past of the years is that we started from that, which was mostly an ergonomic design. And as the technology progressed, we moved to something like that, which gave to the subjects some more autonomy on what they were able to do and to do by themselves. And we ended up to something like that, which is for me the epitome of what an assistive device should be able to achieve. So what has really changed in between those three models is the level of personalization of the assistive device. And Taking a closer look to Professor Hawkins' wheelchair, we can see that consists of a set of different highly customized designs that help this specific bright individual bright in what he loved to do. But these components were specifically designed to offer the optimal user experience to this person. However, as I said, these are highly custom designs, and as you can imagine, they were highly expensive. And the thing is that not everyone can afford a $500,000 device. And that's where AI and machine learning comes into the discussion. How modern AI, how AI and machine learning can help modern assistive technologies learn from generic patterns towards designing more personalized scenarios. So first of all, let's see how we can collect data. And there is a bunch of ways of doing that, each of them coming with their pros and cons. So there are wearable and mobile sensing ways of collecting data. There are off-body and contactless sensing, and where we usually refer to different types of cameras, such as near-infrared cameras, telmar cameras, or regular cameras, and microphones. There is the medium of interaction itself, where it can give us valuable information about the way the subject interacts with the environment. And there are, of course, self-reports, where we have the users giving us their personal view of a specific condition that they experience. And as I said, each of these data acquisition approaches comes with pros and cons that are mainly decisions that have to be made by the engineer beforehand, so they can make sure that they meet their expectations. In terms of wearables, there is usually an invasiveness versus accuracy trade-off that has to be decided. While in terms of contactless sensors, there is usually a trade-off between privacy and data quality. The more you want to preserve privacy, the less robust your data are, but you really have to preserve privacy, so you need to find an intermediate representation, an intermediate medium to achieve both. In terms of interaction, there is usually a trade-off between interactivity and intentionality, which means the more you fine-grain an interaction scenario, the less freedom you give to the subject to act naturally. Thus, the less realistic is probably your assumptions, but at the same time, the clearer are the data that you eventually are going to get with less noise. Lastly, when it comes to self-reports, in order to robustly represent a problem using self-reports, you have to collect many of them, and usually in a high frequency. That can end up being quite invasive for the subject who is using the device at hand, and that might lead to them dropping the study or not using your technology anymore. So these are balances that have to be found when designing a study and given what the scope of the study is. But even after collecting the data and making those decisions, there is a bunch of other challenges that have to be addressed that relate with how the different kinds of data should be merged and fused, how you are supposed to identify and discriminate meaningful patterns from patterns that are not that useful, how to clean the noise from the data, how to deal with missing data, and with insufficient amounts of data, which is a highly common problem in this area of research, and how you can develop trust with your subjects so they can, recommend your study to others and keep using whatever technology you want them to use. So the way of collecting data and presenting the results has not really changed over the years, and that's what I'm trying to show in this slide. This figure here on the left was initially designed in 1993 and tried to show how we can first collect and then process and visualize the data to the end user. And that's exactly what this picture from the Intellimedia group at North Carolina University tries to show in a much more fancy and way, in a more recent representation. So the concept is that we usually collect data either sequential or in parallel, and we process these data and present them either by combining them or independently. And that is highly dictated up by the nature of the task that we eventually want to achieve. To highlight those differences, the following couple of slides aim to show how different approaches dictate different tasks, dictate different modeling approaches. So this is a study I've worked on back in 2015, where we tried to analyze sleeping behavior of subjects. At this time, wearable technology was not that popular at all compared to what it has become today. And what is mostly interesting about the study is that we try to do similar things that today's wearable technology does, following a completely different route without using wearable technology. So these are, we used two completely contactless sensors. One is a pressure mat that was under the bed, and the other one was a regular webcam attached on the side of the bed. And what we tried to do was to process these two different sensors independently to create a detailed report eventually to the subject that we presented in a mobile app about their sleeping behavior and routine. So we used the pressure mat to analyze the sleeping posture, and the camera to detect breathing activity and monitor their periodic breathing activity, and also detect abnormalities in case they stopped breathing occasionally and send alerts to the device. We also used both of the modalities to create a joint graph representing the their motion levels overnight. So this, as being a more abstract scenario in the sense that different subjects react completely different in their sleeping routine and in the way they react during sleep, we decided that processing each modality individual and giving a more detailed report to the subject for them to interpret themselves had more meaning compared to this study, where the goal was to detect and monitor fitness activities. So fitness monitoring is a much more fine-grained area where each exercise has to be performed in a specific way. So in this case, we used two different sensors. Again, we had a regular webcam, this was an in the wild study. So each participant performed the activities on their own homes using their own devices. And we had an accelerometer attached on smartphones and a regular webcam, whatever its participant had at their homes. But in this study, it made more sense to use the modalities in combination towards providing a more effective and robust outcome out of the study. And we can see that because these are the patterns and the representations learned from the two different modalities for different exercises. This is the visual modality, and this is the different features tracked from the accelerometer modality. And what stand out here, and which intuitively makes a lot of sense, is that different subjects had very common patterns when doing the same exercises, something that wasn't the case in the sleep scenario. So the way you collect and process data makes a big difference depending on what you're actually trying to achieve. This is another study we did a couple of years ago, and what I'm really trying to show here is how we can learn from things, from data that come from very diverse groups. So what we tried to do in this study was to detect emotion, but the catch is that we tried from speech, but the catch is that we tried to do it in a language independent and a linguistic independent manner. So we compiled a big data set from using online freely available data sets plus our own data set from around 10 different languages. Most of them were Italian, German, English, and our data set, which was a data set compiled by segments from movies, had movies from all around the world, including Portuguese, Spanish, and other languages. And we try to detect emotion when in an unknown language, let's say. Even though this approach at the time produced results directly comparable to state of the art, but what was the most interesting was that even though we weren't able to show use this model as a plug and play model in an emotion detection task, it was very clear that there were underlying similarities in the speech patterns observed in different languages that no human could observe just by listening the samples. And this is, I think, this highlights a lot the fact that we can learn from a lot of subjects about behavioral patterns and try to apply that in new individuals. This highlights the promise of the research approach overall. In a more recent work, which is part of my work as a member at Michigan AI, we did this study where we tried to assess stress. And even though stress detection was here the downstream task, the main question at hand was, okay, we can detect all these different behaviors using all these different modalities, but do we always have to build a unique pipeline for whatever scenario we have, for whatever modality we have? Because this is, of course, very manpower consuming and time consuming and expensive. So we tried to experiment with that, and we proposed two different architectures. The one was an architecture that could be used as a plug and play method in different modalities without changing the architecture, but just having to retrain the architecture on the new modality. And the other one was an architecture that you were supposed to train once and apply it in parallel in multiple modalities. So the architecture was supposed to create a representation for each modality individually, align these modalities in the temporal domain, learn their temporal representations, and eventually provide the modality agnostic representation that could be used for the whatever downstream task we had. So what we found, at least based in this preliminary analysis, was that indeed modern machine learning and deep learning in this case, or slightly deep learning methods can be used in a plug and play manner across modalities. And even though not all modalities are quite informative, combination of those or some of those provided very promising results on the task of stress detection itself. Merging all modalities together, though, proved to be a much more challenging task because, as you see here, there are many different tasks that have to be taken care of. So the fact that a lot of data also is needed proved to be a big obstacle to merging all together in a single architecture. However, it was still better than just using everything beforehand and passing it through a model once, which is what these results indicate. And this is the model approach here. So here we saw some different methods of acquiring modalities, processing modalities, and presenting modalities in a way diverse enough to capture the different signals generated by humans in their interactions. However, even though in some cases that can be enough in an easy task, in many cases we can do much better than that. So what usually happens when it comes to personalization and building more personalized models is that we have this initial knowledge base where we build a task-specific but user-independent model using either a supervised or an unsupervised approach, and we use this model on a new user. That's what most of the applications we saw so far try to do. However, when it comes to personalization, what we try to achieve is collect more user-specific data, integrate it to the model that we already have, update the model, and gradually make it more tailored to the specific user's actions and performance. We don't want to overfit the model with users' data. We usually want to keep some of this generic knowledge there to make our model more robust, but the overall pipeline looks like that. So there are different ways that we can do that, and this is one of the works we proposed in the past, where in this case we have, in this specific scenario, we have someone imitating a robot performing some yoga postures, and there is a domain expert observing this interaction. So eventually we have three sources evaluating the interaction itself. The one is a sensor monitoring the physiological signals of the subject. The other one is the Kinect evaluating the performance of the subject on actually performing the postures in the correct way. And lastly is the domain supervisor, who is the human supervisor who has the domain knowledge and the expertise and the experience, and can provide feedback on how well this interaction is being performed towards the benefit of the user. So combining these three devices, we can form a state that describes the quality of the interaction at each point. And this state can be then provided as feedback to the adaptation module that works using an RL agent in this case. And this RL agent can dictate to the now, in this case, for what is the best next optimal position to do in order to achieve, to better achieve the task of the subject performing well to this yoga session. This is very well on creating personalized models in general, in theory. However, it has some big problems. The first one being that it needs a ton of data to be trained, and you have to keep the user motivated to keep providing those data until your model adapts. Also, adaptation is relatively slow, and it's very hard to evaluate because the actual evaluation you have is from users giving their own subjective feedback on how well they perform. So a more modern approach on building personalized models and learning more personalized insights is this approach, which is probably one of the more popular approaches on personalization and machine learning at this point, where it's a deep learning based approach where you have the first layers of the model learning more generic features that are being applied across all different groups. And the last layers of the model learning more group specific features and trying to model better those clusters. So these layers are learning from errors being propagated by all the neurons of the network, while these layers at the leaves are learning mostly by errors being propagated by data coming from subsets belonging in this specific group. Very similar to that is this approach, where again we have the generic feature and the individual feature section, but instead of groups, we have actual individuals here. The problem with this is that it's very hard to scale up because, as you can imagine, if in a realistic scenario we have hundreds of thousands of users, first of all, the error being propagated to these initial layers, it's much more noisy. And that's especially true for users that interact with the system significantly less compared to others. But still, it's the same architecture. Another approach, very recent, published in 2020 by a group in Texas A&M, is this, again, deep learning approach where a Siamese network is used. Siamese networks use pairs of data. And what the network tries to actually achieve is to increase the distance between representations of subjects belonging to decrease the distance between the representation of subjects belonging to the same cluster, to the same group, and increase the distance between representations of subjects belonging in different groups, thus creating unified representations, if you prefer, on subjects that have more similarities together. How do you design these clusters in the first place? Usually using some unsupervised clustering approach on some criteria depending on the task. For those interested in those tasks, these are some useful research, very recent research that I would like to suggest. And I think I want to say that this is a very evolving task, both of them, both learning from multiple modalities and also designing personalized scenarios. And there is no problem solved there yet. My personal research has been focused primarily in concepts related to fatigue, distraction, and cognition. And I would like at this point to show you a video that is primarily related to most of the research I did under my PhD. And for this paper also we received, for one paper related to this study, we also received the best paper award at IUI, ACM's IUI in 2017. And let me go ahead and change the screen I'm sharing and show the actual video. So, a second.
The Activate test of embodied cognition is a revolution in how we measure neurocognition. For a generation now, neuroscientists have been moving forward with their understandings of how the brain and the mind work. But neuropsychology and neurocognitive testing has remained far behind, in part because we didn't have the opportunities that are now possible through the application of motion capture technology. The reasons we want to measure embodied cognition is because we believe that a measurement of embodied cognition will be much closer to how people function in everyday life. The comprehensive assessment that ATEC provides includes balance, it includes rhythm and coordination, it includes response inhibition, sustained attention, processing speed, motor movement, and more. As an interim step to create an automated scoring system which will be 100% reliable because it will be based on motion capture analysis and algorithms, we needed to create a manual scoring system. Our early results show that the Activate test of embodied cognition produces scores that are very strongly related to the behaviors of children functioning in daily life. One of the lovely things about the Activate test of embodied cognition is it doesn't take a great deal of fancy equipment or specialized space to use it. What occurred to me was that we could invite the child to participate in a television game show with other children, in which there would be a host. And that game show would be recorded, and the host of that game show would give the instructions. Every child, every time, would get the same instructions. The ATEC system is just a computer and a couple of Kinect cameras set up to capture a couple of views of the child as they're doing the activity. And it needs to be a space large enough for a child to be able to walk 10 paces. So you have a screen where Eliza is giving the instructions to the child. There is a person in the room, a technician, who has a tablet with a GUI interface, a graphic user interface, and he pushes a button on the tablet, and Eliza appears on screen and gives the child the instructions. And perhaps in the instructions, there's also one of the Activate kids who comes on and demonstrates it. Then that segment ends, and the technician asks if the child understands and makes sure that the child is in the right position and ready to go, and then pushes another button, and Eliza administers the task itself. And when that's over, we move on to the next one. But the great advance will be to be able to have this system fully automated using the motion capture technology and the algorithms created by my colleagues at University of Texas Arlington. What this will mean is that a child can come into the room, participate in the Activate test of embodied cognition, and when he walks out of the room, there can be automatic scoring of the behavior that occurred in the room. And this will be done without the need of a person sitting down and laboriously scoring videos. It is with children that we are most eager to have assessments because...
And at this point, this research has been much progressed, and many of the tasks are actually being now automated, and the whole system is being applied in several schools across Connecticut. As you probably saw, this was a work in collaboration with Yale University and Psychiatry Center Department. And similar to that, most of my recent research interests have to do with, as I said, cognition, fatigue, and distractions. So in recent years, we did several studies trying to learn robust representations of physical fatigue and try to correlate signal representations to actually subjective user reports and see how much of generalization is there. We tried to use EEG signals as a feedback signal to either measure engagement of a specific user in a subject, or use these EEG signals as a feedback to predict future performance on a cognitive task. I've also spent some time building tools and data towards detecting cognitive fatigue using, again, multimodal data. Unfortunately, these are a lot of studies that I wouldn't have time to go into further details into them. But the concept is always the same, how different modalities can be used and correlated with different types of data collected towards learning robust representations. One of my most recent works is in collaboration with some colleagues at on detecting driver alertness. This is a work done also in collaboration with Toyota Research. And we have this data set where we collect a bunch of different data, very rich data set, which we hope soon to publish also. And we have some preliminary results that you can find in this paper related to how we can discriminate between distracted and drowsy driving and combinations of those classes. And we have some very cool and interesting results coming up very soon, which unfortunately I can't share yet as they are under review. But stay tuned. So wrapping up on how we can process and collect data, I would like to discuss a bit on what we do after we collect this data. And there is a big limitation on how we interpret this kind of data. So there are usually two different battling schools at this point. The one is the traditional machine learning and statistics school, and the more recent one is the deep learning based approaches. My view on this problem is that both approaches have big pros and cons. With the tools provided by traditional machine learning methods being extremely useful and valuable towards actually understanding what you're dealing with. Extracting signals, doing signal processing, and designing hand engineering features and learning statistics about your data set can give you great insights about what biases are in your data, what of the features you designed are redundant, which are not, if there are information that is actually causing noise on your data, and many other insights. Same comes with more traditional and simplistic machine learning models, such as Bayesian or tree-based approaches that can be easily interpreted and explained through some kind of metric that they use to optimize. On the other hand, on deep learning methods, there is usually a vast model that comes and breaks the curve in terms of performance, which is great, but it's harder to learn insights out of it. Learning insights about the data set through traditional methods can also help us a lot towards designing more efficient optimization functions for eventually whatever method we're trying to use. The problem with deep learning architecture is that at best, in a computer vision task, we can see what the network learns over time by visualizing some of the features, if that is possible. But in other cases, that is not even possible. And there are some visualization of feature maps learned by network from a research work I did on speech-music discrimination in the past. So in that case, the network broke the curve, provided literally state-of-the-art results at the time. But as you can see, the representations learned are really not intuitive at all. So it's really, we really need to have a balance, I think, between how we use methods that have traditionally proven to be valuable towards understanding the domain we're working on, and how important it is performance to us. A recent way of evaluating deep learning models is probing task. And in particular, a probe is trained to predict properties we care about from representations of a model whose nature we'd like to know more about. What we mean with that is that we have some learned representations on a downstream task through a deep learning model. At the same time, we are able to get some labels on a probing task from the data that we have. Thus, we are able to train a new model, using these new representations and the probing labels that we have, and evaluate the performance of these representations on the probing task. If we get a good performance, we can assume that these labels, this probing task was probably important towards performing, towards a specific performance in the task at hand. Let me give you an example. We have a part of free text from some individual, and we want to see if there are signs of anxiety in their way of writing. We can learn a text classifier directly detecting behavior, patterns of anxiety through the text, but we can't really learn what were the individual components that drive the model to make the decisions it made. However, we know what part of speech the individual words are from their script. And we use these labels and train a probe task where we use the learned representation from the anxiety task to classify part of speech tagging on the words. If that performs quite well, we can assume that knowing the part of speech for the different words was an important task towards detecting, an important feature towards detecting anxiety. I use the NLP examples because this technique is fairly new and has mostly been applied in natural language processing domain, which is fairly intuitive on how to be interpreted, and is being slowly expanding in other domains, mostly in vision, but hasn't been yet moved, explored a lot in physiological representations. And the main reason is that they are much harder to understand and interpret just by visually observing them. However, I can definitely see that the future is going towards there. And at the bottom, you can find some interesting leads related to how we can use probing to interpret insights about deep models. And model interpretation is one of the most important things in this area of research. Before I finish, a few more things, some things about data collection. So there is usually a trade-off between collecting data in a lab and into the wild, and there are always some pros and cons. In-lab experiments are usually harder to collect larger amounts of data because you need to have people coming into your lab, and the assumptions you can make out of it are usually less robust because you have a very controlled environment. However, you get better quality of data because the environment is more controlled. And you have more options on what types of data you're going to collect. It's easier to preserve privacy as everything is being stored directly locally in the lab machine. And is generally cheaper because the same equipment is usually used again and again. However, doing experiments in the wild is usually easier to get more data because users can just provide you their data while involving in their daily routines. And it's the data you collect are more representative of their actual daily livings, which in some cases that's very important. However, they are at the same time very noisy. There are a lot of missing values. Users they don't get involved in the task. So this is a big trade-off. And the data acquisition options are usually limited as you have to go along with sensors and devices that are not obtrusive in their daily routines. There are greater privacy concerns on how this data are going to be processed and transferred to the units that are going to be processed eventually. And it's usually more expensive as more sensors usually needed to be distributed to the different subjects. Devices break or get lost easier. Participants disappear, and you never see your equipment back, and several things like that. Another problem that is very common, especially when dealing with deep structures, is the lack of data. And usually a way of dealing with this problem is by doing some kind of data augmentation. So what data augmentation is, that is a way to create artificial samples based on a smaller data set you have of real samples towards describing underrepresented scenarios in your data set. And that can be extremely useful and valuable if it's done right. And in order to do it right, you need to really understand in depth what is the task at hand and what are the modalities that you are using. In more abstract modalities, like such as physiological signals, this is much more difficult and needs to be done really carefully because it's quite easy to introduce biases in whatever approach you're following and derive results and assumptions that are completely unrealistic just because you have biased your data through your data set through your augmentation. Last but not least is building trust with the participants we have. This is one of the major problems in the sense that finding participants in the first place in human subject studies is a big deal, and it can be very difficult. So very briefly, in my opinion, it is very important to clearly explain to the participants what is the purpose of the study and what sensors have to be used and in which way. And if there is a goal to publish the data set eventually, how the data are being stored and processed and how you're going to preserve their privacy. These are very important questions that need to be addressed and clearly explained. For various reasons. First of all, because they are important in general. Secondly, because when the users understand better what they're dealing with, it's more likely for them to keep using and participating in your study. And also, it's more likely to introduce more users in your study, which is something that we really need. Also, it helps with the process of IRB if you want to make some change down the road or use the data in a new way that you didn't have thought before. It makes things easier if everything is out clear and everyone knows about it beforehand. So to sum up and finish, we talked about initially human behavior and how complex it can be and how multidimensional it can be. And we discussed how much of a central component is towards designing any kind of assistive technology, which their purpose, on the other hand, is to enhance human performance. Well, we saw how multimodal monitoring is very important towards capturing diverse signals of interaction and how processing and visualizing those signals can really make an impact on the experience of the interaction. And we saw how we can go a step further by using personalization in our models and using specific algorithms towards improving the user experience and the personalized interaction over time. At the end of the talk, we discussed a bit the different obstacles and problems that we need to address and that they are still under topics to be researched. They mainly refer to data collection approaches and problems, or data and model interpretation. So you can find a lot of data sets and implementations in the following links. And if you have any questions, feel free to reach out. And thank you so much. I don't know if I took more than I had to.